work with Pierluigi Nuzzo, Mehdi Masumi, Yuxun Zhou, and my advisor Alberto Sangiovanni Micentelli. As we know, the basic objective in power grid operation is keeping the balance between supply and demand. But due to the deeper penetration of renewables, this task has become more and more difficult to achieve than before. So in the scheme of demand response, we want to exploit the demand side flexibility for keeping this balance. So the two basic requirements of demand response are responsiveness, which means how accurate and how the demand response can react. The load can react to the demand response requests. And the other requirement is non-disruptiveness, meaning that the demand response should not affect the end user use too much. And there are two basic mechanisms for regulating the demand. The first one, as its name suggests, price response uses economic incentives to regulate the demand. It tends to be less disruptive to the end use because the users can adjust their power use according to the price, and is thus more widely adopted in today's power grids. The other mechanism is called direct load control. In this scheme, the demand is directly regulated upon the grid operator's request. So it is possible that this scheme may disrupt the end use and making it harder to deploy in power grids. However, this scheme has the benefit of being more responsive at smaller timescales, especially in small, like faster than 5 minutes, and thus it's more suitable and necessary to handle the fast fluctuations injected by renewables. And it is also a challenge to aggregate heterogeneous components in demand response. So we have seen a number of previous works in aggregating homogeneous, that is the loads of the same type. For example, a large number of electric vehicles or lightings, these demand response resources. So these approaches usually depend on a mathematical model, either deterministic or stochastic, of the aggregate behavior of these demand response components. And based on this model, we can derive a control strategy to optimally manipulate these devices. However, in the heterogeneous case, the aggregation is even harder, because one of the reasons being that we lack a unifying formalism to describe the behavior of each individual load as well as their composition. So in this work, we propose a contract-based methodology for aggregating heterogeneous demand response resources. So in recent years, contract-based design methodology has emerged as a formal methodology for designing cyber-physical systems. Contract-based design has the benefit of the traditional, maybe you have heard of component-based design that utilizes the modularity of different components, and platform-based design. So when designing a complex system, we wish to reduce the complexity of design and verification by decomposing a big system into smaller ones. And especially, we wish to find a suitable abstraction for each component, as well as a unifying representation of their interface, and a specific kind of contract-based design, a specific kind of contract called assumed guarantee contract, give us that benefit. So an assumed guarantee contract is a triple of component variables, as well as the assumptions and guarantees. So the assumptions and guarantees are assertions representing sets of behaviors over these component variables. So the assumptions encodes the what the component assumes on the environmental behavior, and the guarantees is the behavior that can be provided by this component under this assumption. And let's have a look at this of the proposed demand response framework. So we have our aggregator runs a aggregator MPC, which is an optimization scheme that so at each time instant, it will receive a demand response request, which can be thought of as a reference signal, but it gets updated at each time step. So the objective of this of the aggregator is to track this signal. And the C sub 1, C sub 2 to C sub n shown here are demand response components. So at each time step, it will expose its interface, that is the contract, to the aggregator. And based on this information, the aggregator can compute the best strategy to control these components over a finite future horizon. And this procedure is, this MPC is solved repeatedly over time in a receding horizon manner. Okay, let's look at two more concrete examples. So we have a water pump shown on the top right corner. And to specify the water pump, so as we know, the water pump consumes power when water is pumped into the tank, and it can generate power when if we release water out of it. So to specify this water pump, we need to know how fast is the water pumped up or released, and how much energy is consumed or generated in both cases. And also, there's several constraints, like the water level. The amount of water should never exceed its maximum and minimum. And we also have a minimum on-time constraint. So this constraint here means, so if we switch from the idle state, which means the water pump does nothing in this state, to the generation state, we need to stay there for at least some certain amount of time before switching back to the idle state. So this constraint here avoids the water pump to frequent switch between working modes. So the contract of the pump can be compactly expressed as a discrete hybrid automaton shown here. And let's express the behavior of the water pump over a future horizon by converting this discrete hybrid automata into sets of mixed integer linear equations as shown here. So the assumptions made here is, so we use these constraints. So this is an example, not all of the constraints, encodes the allowed input from the environment from the current time step to a finite future horizon. And these constraints below are the guarantees that can be provided by the water pump, including its dynamics, both the discrete state and the continuous states, as well as the ancillary power output. And another example here is more realistic. So as we know, in HVAC systems, the fans has the flexibility to ramp up or ramp down. So it also has the potential to provide ancillary service to the grid. Since the zone temperature is not sensitive to fast changes in the supply airflow, that is, so it can be expected that if we have carefully designed fan schedules, we can exploit the flexibility within the fan power consumption without compromising the room temperature as shown here. So, okay, let's derive. So this figure here shows the contract of the fan, so which is actually the power consumption bounds of the and as well as the baseline power consumption of the fan over from the current time step to h steps in the future. Similar as in the previous case, we have a set of assumptions, which encodes like the ramp rate constraint. That means the power consumption or the fan speed between two subsequent states cannot exceed a certain number, as well as the bounded control input. And we also have this set of guarantees. So this set of assumptional guarantees encodes the interface exposed by the fan to the aggregator. So we may be wondering what procedure decides the set of the interface exposed by the fan. So here we use a approach proposed by Masumi a year before. So he uses an MPC approach to decide the bounds as well as the baseline. So the idea being we can receive a reward for providing flexibility to the grid, but we also need to pay electricity prices for consuming power. And this MPC here actually minimizes the net cost, which is the difference between the cost and reward. And here we also have the affinity law, which expresses the relationship between the fan power consumption and the fan speed. So I want to remark here that this approach used here is orthogonal to our framework, because we can also use other approaches to compute the bounds. And so here is the proposed control synthesis flow. We have a library of DR components as well as their contracts. And we also have the top level DR contract, which specify the requirement on the aggregate response. Then we put all of these things together into a mixed integer programming problem, which gets solved repeatedly over time in a receding horizon manner. Then we get the control strategy. To be more specific, we can use parallel composition. So in this case, it's just juxtaposing all these mixed integer linear constraints of all those DR components together into an aggregate contract. We also have an interconnection constraint. So here it means the total demand response is the aggregate, is the sum of each individual response. And here we also specify the cost function. So this is an example of the cost function, and we can also take other factors into consideration. So, and rho, the rho h shown here means the predicted future trajectory. And our goal is to use an optimized mapping problem to find the best optimal control action that can minimize the cost function. So we did a case study consisting of 3 pumps and 4 fans to see how this system actually works. So we use YAML as the specification language for the contract for each component, and Gurobi as the MILP solver to derive the best strategy. So here is the simulation results of the pump. As we can see, the pump, as well as its the water level and the time counter, works exactly the way we specify it. And for the fan, so for more accurate results, we use a nonlinear model for the in the simulation for simulating the temperature evolution. So as we can see, the red trace is the actual power consumption of each fan, and the green and blue are respectively the upper bound and lower bounds of the ancillary power. Although there are times for each individual fan that they cannot provide any flexibility, but for the aggregation, we still have some flexibility. And we can also see that the temperature of the 4 control zones in the simulation all stay in the comfort zone. Okay, let's look at the aggregate response. The red trace is the aggregate response produced by all 7 components. And the blue line is the tracking error. And we have, in this simulation, we achieved a mean average tracking error of 9.32%. And the type-wise aggregate responses is also shown here. So to sum up, in this work, we propose a framework for aggregating heterogeneous demand response resources in smart grids. Especially, we use a formal contract as a unifying way to specify the requirements, as well as the interface for heterogeneous demand response components. For future work, we plan to look at, to apply this approach to more complex situations with more components, as well as more complex interfaces. As we know, this MILP framework may result in a very big optimization problem, and possibly we will also look at some relaxation techniques for better handling them. And also, as we have seen, the interfaces here are deterministic in the current framework, so we are also planning to look at statistical models for modeling their interfaces. So that's it for my presentation, and I'm ready for questions. Thank you.